Hi everyone, welcome to my channel. I'm so happy that you're here with me today. There's something that intrigues me a lot. So last week I was in Berlin teaching deep learning for computer vision, and before that teaching deep learning for natural language processing. And usually when I'm teaching, I do not have time to update myself on what's going on. There's a new paper, a new large language model. A new kid on the block, LLaMA, Meta AI, just published it recently, 17 hours ago. There's a new open source high performance language model called LLaMA, llama. I think it has to do with the animal, right, from South America. I'm very curious. And what really captures my attention is in the paper, and boy, we are going to have a look at the paper, it says it's open and efficient, which I like a lot. I mean, open is a great thing because, well, you remember the, let's say it, the disaster with OpenAI, where they started as a company that wanted to open AI to everyone. And then it turned out that, well, up until today, those models that we would love to use, OpenAI's GPT family, is not really open. You have to pay for it, which, well, it's fine. It's a company. They have to make money. And I think there's only one exception, the Whisper model, which is freely available for speech to text transcription. Okay, well, not so many neural networks are available so that you can download them and turn them into your own prototypes and even products for the good of all mankind. Efficient is also another very, very interesting thing because we remember those large language models. They're really, really large when it comes to the sizes. I mean, trainable parameters is one number that we always take into account. And also they are large in inference. It takes some time to do a prediction. Definitely something that we have to take into account nowadays. So it's always the question, can you run it locally? Can you run it on your GPU cluster? How long does an inference take? Coming back, there was this really, really nice announcement on Twitter by LLaMA recently. And when we have a look, there are also a couple of blog entries introducing LLaMA, a foundational 65 billion parameter large language model. 65 billion, comparatively much. In comparison to GPT-3, not that much. GPT-3 has 175 billion trainable parameters, so it's significantly smaller, round about a third, give or take a couple of billion trainable parameters. There's a paper available. We will have a look at the paper first, and then we will talk about the quote-unquote openness of this neural network. There's a model card available, and you can apply for access to this large language model. There's another blog post. I think I'll post the links all in the description of this video. Quite fine. But first things first, let's have a look at the paper. Let's see what we can learn from that. Okay, let's start with the paper. LLaMA, that's the name of a neural network. It says that it's open. Well, we have to talk about that one. And also that it's efficient and it's a foundation language model. Language models, very easy to explain. Natural language processing, so everything that has to do with text usually is a language model. Foundation model, here the idea is that you have one neural network that you can use to, well, let's say, solve all your problems, all your use cases. So train one neural network on everything, and then you can do quite a lot of exercises with that one. Here, a great group of people from Meta AI, all very appreciated. Let's dig deeper in the abstract. We introduce LLaMA, a collection of foundation language models ranging from 7 billion to 65 billion trainable parameters. Now think about this. Okay, how much is this? Comparison to GPT-3, very interesting, 175 billion trainable parameters. This is rather big in comparison. There's also Chinchilla available, 70 billion trainable parameters, and Palm, 540 billion trainable parameters. So we train this neural network, we train our model on trillions of tokens, which is, boy, quite a lot, and show that it is possible to train state-of-the-art models using publicly available datasets. Publicly available, that's cool. So nothing that is hidden in some basement, everything that is available on the internet. Very cool, and they trained it exclusively. So they only used that data. Of course, it has a certain advantage when you train on your own data, but I mean, boy, this is something because it tells you that this whole data effort is reduced to bare minimum by using datasets that are freely available. without resorting to proprietary and inaccessible datasets. It's very cool. Proprietary and inaccessible datasets, very important. And it outperforms those networks mentioned on most benchmarks, which is cool. So they tell us that they have a neural network that is open and that is efficient, that is smaller, and outperforms other neural networks, all other competitors on the market. Yeah, and then comes the introduction, so on and so forth. Large language models trained on massive corpora of text. That's quite fine. Couple of resources. The objective of scaling laws of Hoffman, and so on and so forth. Hoffman et al. Recommends training a 10 billion model on 200 billion tokens. And we find that the performance of a 7 billion model continues to improve even after 1 trillion tokens. This is very interesting. So you see me skimming through this paper. This is not going to be me reading the entire paper to you. It's just trying to find out what are the most important things. When we talk about transformers, there is one thing that I find extremely amazing and that still puzzles me up to today, that those neural networks are very efficient when it comes to training. So usually, and so I saw this with my own music models, that you can train it on a lot of data with just a few trainable parameters, and it still works. And usually you don't have to present the training samples multiple times. You train it one epoch and everything is fine. So there are people who suggested, well, there's a certain direction where to scale, but in this paper they found out that even smaller models, they still perform better and better if you train them on more and more data. So they're very, very, I can say, very hungry for data. It might be the case, and I think this is what I'm getting here, I'm reading between the lines, when we think about GPT-3, which has been trained on 500 gigabytes data, 175 billion trainable parameters, so rather brute force, and maybe it wasn't really effective. Maybe they could have trained it on even more and more and more data, and nobody knows yet how much data. The focus of this work is to train a series of large language models. That's what people usually do in writing a paper when preparing, that they start with an architecture, with an idea, and then they scale up. Looks like to me they are just scaling up the neural network architecture, not the dataset size. Okay, ranges, those are the parameters. We already saw this in the abstract, 7 billion to 65 billion trainable parameters, with competitive performance compared to the best existing LLMs, which is cool. Same performance, smaller model, faster inference, cost for hosting is smaller. It outperforms the 13 billion trainable parameter, outperforms GPT-3 on most benchmarks, despite it being 10 times smaller. This is really, really cool. You can do the math, like how much money you will save if you run a smaller model. You need less hardware, and it doesn't take that much time, because all your tokens don't have to go through 96 layers. Maybe it's just a fewer layers, maybe just 10. I think it's more than 10. We believe that this model will help democratize the access to the access and study of LLMs, which is good. So give everything to the people. It can run on a single GPU. Boy, I want to try this out. And then they have, at the higher end of the scale, of 65 billion parameter model is also competitive with a large language model such as Chinchilla or Palm 540 billion. Well, it's quite something. Unlike Chinchilla or GPT-3, we only use publicly available data. Again, what we saw in the abstract, making our work compatible with open sourcing, which tells you that you can do the same exercise. Assuming that you have enough GPU compute, you would download and pre-process the same datasets. You would download the neural network architecture, not the trained models, and then you would train it maybe for a couple of days or a couple of weeks, depending on how much GPUs you have available. Competitive and so on and so forth. In the rest of the paper, we present an overview of the modifications we make to the transformer architecture. Now here, gets very, very interesting, at least for me. So the transformer architecture, Vaswani 2017, Attention is All You Need, the seminal paper that opened the field, or that showed that, well, boy, self-attention is very, very effective. What people then did after the release is they split it in two branches. One branch was the BERT branch, or still is the BERT branch, language modeling for masked language modeling, and the other is causal language modeling, predicting the next token autoregressively with GPT and GPT-like models. And I guess that LLaMA, because they compare it to GPT-3 and so on and so forth, is a decoder-only neural network. So not sequence to sequence, only using decoders for language generation. We then report the performance of our models and compare them with other large language models on a set of standard benchmarks. That's cool. Finally, we expose some of the biases and toxicity encoded in our models. It definitely comes from the datasets, using some of the most recent benchmarks from the responsible AI community. So this is cool. So they took the original transformer architecture, they did some changes, still training on the same datasets. There's some biases and toxicity in it. Very good to have a look at this. Cool. Our training approach is similar to the methods described in previous work and inspired by the chinchilla scaling laws. We train large transformers on large quantity of textual data using a standard optimizer. The optimizer is the training algorithm that is used for stochastic gradient descent. And here, well, no new optimizer developed, just a standard one. Makes me very, very happy. Pre-training data. The plot thickens. Our training dataset is a mixture of several sources reported in Table 1. Beautiful. That cover a diverse set of domains. For the most part, we reuse data sources that have been leveraged to train other large language models with the restriction of only using data that is publicly available. Again, publicly available data and compatible with open sourcing. This leads to the following mixture of data and the percentage they represent in the training set. English Common Crawl, well, the entire internet, at least the English side, 67% of the data set. C4, it's another data set available. Here it's 15%. GitHub, this I think is source code. It's very, very interesting. We learned recently, well, for me, it was the first time that I heard this in this great idea from Lex Friedman, that if you train a large language model, not only on language, but also on programming language, it gives it a very, very good boost in reasoning, sequential reasoning as well. A computer program is something that is sequential in nature. And here you would teach the neural network to be a sequential thinker. Wikipedia, 4.5%, cool. Gutenberg and books, so book, literature, archive, papers, Stack Exchange, also something for question and answering. They trained a tokenizer. That's very, very crucial piece in the puzzle. Tokenizer, it's trained in a sense that it learns something from data, but not in a sense that it uses stochastic gradient descent. It's not a deep neural network, still it's a statistical approach. And the idea of a tokenizer, as we all know, is to take any text and map it to tokens. And those tokens are the sequences, or form the sequences that our neural networks predict on. Cool. Overall, our entire training dataset contains roughly 1.4 trillion tokens after tokenization. So taking all the strings, all the text, running them through the tokenizer gives us 1.4 trillion tokens, which is quite a lot. For most of our training data, each token is used only once during training, which means most of the training data, one epoch of training, with the exception of Wikipedia and books domains, over which we perform approximately 2 epochs. So it means okay, they appear double in training, but we learn, well, not training 100 epochs, we train this on average or even more for 1 epoch. Architecture. So far we heard about the data, which is quite cool, quite a lot of data, tokenized. And now, what kind of model architecture do they use, or what are the differences to already existing architecture? Following recent work on large language models, our network is based on the transformer architecture. That's nothing new. GPT something. We leverage various improvements that were subsequently proposed and used in different models, such as Palm. Here are the main differences with our original architecture and where we found the inspiration for this change in bracket. Couple of changes, 1, 2, 3. Pre-normalization, and they got it from GPT-3. To improve the training stability, we normalize the input of each transformer sublayer instead of normalizing the output. Okay, when you look at the original paper, attention is all you need. You will see the encoders and the decoders of the transformers explained, and they have a couple of things. There's the multi-head attention in it. There are also multi-layer perceptron layers. There are skip connections, and there is layer normalization. In the original architecture, the layer normalization happened at the end of each decoder. And here they suggest, following the paper of GPT-3, to use the normalization at the input of a layer. So normalize first and then going through the layer itself, which is quite cool. Then they use the sweet glue activation function, and this idea they get from Palm. So usually, when I teach deep learning, I usually tell, if you have a hidden layer, go for ReLU, which is like almost a de facto standard for deep learning, but it's not, it's not the end of the story. We replace the ReLU nonlinearity with a sweet glue activation function introduced by Shazier in 2020 to improve the performance. And then also rotary embeddings. This they get from GPT-Neo. We remove the absolute positional embeddings and instead add rotary positional embeddings introduced by Su et al. 2021 at each layer of the network. Okay, moving away from the predefined or even pre-trained, the predefined positional embeddings, rotary embeddings. And they have something in table 2. Let's look at this table 2. Very beautiful. N tokens. So seems to me the first they trained on 1 trillion, 1 trillion, and here 1.4 trillion, another 1.4 trillion. Batch size, 4 million samples in one stochastic gradient descent step. They have different learning rates. Okay, it looks like to me learning rate is going down for a bigger neural network. And here comes the crucial part. 1, 2, 3, 4 different neural network architectures, ranging from 6 to 65 billion trainable parameters. Dimension is the size of the embeddings. So tokens get embedded. And then through the decoders, they get token mixed. So the further you go down in the neural network, the higher is the semantic context in the dimensions. So quite a lot. And we also see number of heads. Those are in the decoders, the parallel information flows that we have, going from 32 to 64. And number of layers. So the smallest has 32 layers and the biggest has 80 layers. And then we have a few things in between. So we have layers, we have the attention heads, dimension. And these parameters are usually the parameters that you would use for training a neural network. So here, embedding size, then how many heads, how many layers. This gives you a very, very good a set of parameters for the neural network architecture. And for training, how much data, how big a batch size, usually you max it out, and also the learning rate, how quickly the gradient is going to descend, hopefully not hitting the local optimum. The optimizer is the next thing. We use AdamW optimizer with a couple of hyperparameters, beta 1, beta 2. Cosine learning rate scheduler means that with a cosine function, the learning rate goes down to 10% of the maximum learning rate. They have also a weight decay and gradient clipping of 1, so regularization, 2000 steps warm-up steps, and we vary the learning rate and batch size with the size of the model, as we have seen in table 2. So this is already quite something. So we learned about the data set. And I seem to remember with the data set or data sets, they also tell us what is the pre-processing. So for example, when you go to Wikipedia, you don't want to include the links, so the links are removed. And when you train on LaTeX code, you would remove the bibliography because, well, maybe you are just interested in the content of the paper, not the bibliography, the references. And with source codes, you might be tempted to remove licenses at the beginning or remove source code that doesn't have a high quality. So data's pre-processing. And then we also learned about how the neural network looks like. So what is the architecture? So for people who are into these architectures, who are in the business, it would be easy to understand what to do if they choose to implement such a neural network themselves, use some pre-implementation, and then tune it or train it on their own data. Efficient implementation is the next thing. We make several optimizations to improve the training speed of our models, which is cool, because with those language models, you don't ask like how many hours does training take? It's how many months does it take to train such a neural network, depending on how many GPUs you have. First, we use an efficient implementation of the causal multi-head attention operator. And here we can see this comes from Xformers, also very cool. The problem with transformers, and here I mean the decoder-only transformers, GPT-like transformers, is they have an attention matrix which is masked. And this requires you to, well, it's not a strict requirement, but it tells you you have to manifest the entire matrix and then you mask it, which is very expensive. At the end of the day, the matrix is quadratic in size, and this also affects the inference speed. And this is the bottleneck. This is the upper limit of a sequence length, because you get a quadratic matrix. And here is some speed up for the causal multi-head attention, means it's multi-head attention with a causal mask. This allowing the neural network in inference time to look ahead into the future when it's predicting the next token. It's really, really a great optimization in the original paper, how you can parallelize the training. This implementation available in Xformers, already mentioned here by Facebook, reduces the memory usage and computation, which is good. Speeds up training, you don't lose anything. This is achieved by not storing the attention weights and not computing the key query scores that are masked due to the causal nature of the language model task. That's the optimization itself, but it looks like to me this is available as a module. So if you have your own transformer architecture, your own implementation, you can just plug it in, available in Xformers, and then you get the speed up as well. To further improve training efficiency, we reduced the amount of activations that are recomputed during the backward pass with checkpointing. So activations means those are outputs of layers, and they, during the backward pass, which is the stochastic gradient descent, going back through the layers of a neural network back to the input, propagating gradients, they use checkpointing, which I think translates to that they save stuff on a hard drive. More precisely, we save the activations of the linear layers. This is achieved by manually implementing the backward function for the transformer layers instead of relying on the PyTorch autograd. To fully benefit from this optimization, we need to reduce the memory usage of the model using model and sequence parallelism as described by et al. Moreover, we also overlap the computation of activations and the communication between GPUs over the network as much as possible. So we can see there are lots and lots of optimizations in the model training itself, which I think are books that you can follow, might not be that complicated to DIY. Cool. And then when training the 65 billion parameter model, our code processes around 380 tokens per second per GPU on 2048 A100 GPUs with 80 gigabytes of RAM. So somewhere is a big room filled with 2000 A100 GPUs, each 80 gigabytes of RAM, and they run in parallel to train the neural network. This means that training over our dataset containing 1.4 trillion tokens takes approximately 21 days. Which I think is also another bottleneck for anyone who wants to create that. And that's why it's important that you get pre-trained neural networks from other people. I mean, pre-trained neural networks and transfer learning is one of the best possibilities that we have in order to leverage the whole thing, the whole disaster with that it needs quite some compute. So one of the main ideas of transfer learning is that you train a large, or even fundamental neural network once on as much data and as much data as possible, and then you would give the model to other people to fine-tune. And this fine-tuning is not that expensive. So I believe, for example, GPT-3, I'm not 100% sure about that, but for GPT-3, you don't need thousands of GPUs, maybe it's a dozen of GPUs to just fine-tune it on a few samples. So it translates to everyone can do it, almost all, yeah, everyone could do it. Main results. Following previous work, we consider zero-shot and few-shot tasks. Okay, this is cool. Zero-shot means we provide a textual description of a task. So like this is going to translate from English to French, and a test example, which is something that needs to be filled. The model either provides an answer using open-ended generation or ranks the proposed answers, because they're multiple choice. And the other approach, or the other benchmarks, consist of few-shot, where they provide a few examples of a task between 1 and 64 and a test example. The model takes this text as input and generates the answer or ranks different options. Also cool. Which is also another thing that I like a lot, that they write down exactly how to test your neural network, and then also how to compare this. So assume that you have one way to evaluate your neural networks. You would run each of a neural network that is available, including the other neural networks, those neural networks from other people, and then you see which one comes out top, which is quite cool. We compare LLaMA with other foundation models, namely the non-publicly available language models GPT-3. So either they had a cooperation or they paid for the entire inference. I guess they paid like everyone else. There's Gopher and Chinchilla and Palm, OPT models, GPT-J, GPT-Neo. We also briefly compare to the instruction-tuned models of Optimal and Flan Palm. We evaluate LLaMA on free-form generation tasks and multiple choice tasks. We already read this a moment before. In the multiple choice task, the objective is to select the most appropriate completion among the set of given completions based on provided context. Okay, it's just a repetition of what we've seen before. Cool. So what we can see here, big table number 3. Zero-shot performance on common sense reasoning tasks means description of a task and an example that needs to be solved. And we see here that for those different tasks that, well, I have to admit, I don't know. So just gather there are a few tasks available. That here for the first one, Palm comes out top with 88, and those are the results for LLaMA. For this one here, Pika, it's 82%. So the best model here is LLaMA. So we have one here. Sika, LLaMA, not so many comparisons here. Hellaswag, LLaMA. Vino Grande, not LLaMA. What LLaMA is getting, well, it's not really close. ArcE, LLaMA. ArcC, LLaMA again. And OBQA, LLaMA again. So we see 1, 2 here. And 1, 2, 3, 4, 5, 6. 6 here. And zero-shot performance on common sense reasoning tasks. And in 6 out of 8, LLaMA comes out top. Okay, then we have another one. Natural questions. Except match performance, where we do multi-shot or few-shot. You see here, zero-shot. Different neural networks, natural questions on zero-shot. LLaMA comes out top. One-shot, looks like we have one example, input and output. LLaMA comes out top. 5-shot, LLaMA comes out top. 64-shot, LLaMA comes out top. So out of 1, 2, 3, 4, 4 of 4, this is cool. We have a few more tasks. Closed book, let's have a look at that one. Trivia QA, question answering, zero-shot and few-shot exact match performance on a filtered def set, zero-shot, LLaMA. 1-shot, LLaMA. 5-shot, LLaMA. 64-shot, LLaMA. 4 out of 4. Also cool. Let's go here. Reading comprehension, raise middle and raise high. Here, Palm comes out top with 68. LLaMA fairly close to that one, but does not come out top. And here, raise high. Here we see that LLaMA comes out top, so 1 of 2. We have mathematical, and we have code generation with code eval, human eval, and mathematical reasoning tasks. Let's see, look at this. Model performance on quantitative reasoning data sets. So those are the math things, 1, 2, 3, 1, 2, 3, 4 tasks. Here, not LLaMA. Here, also not LLaMA. Here, not LLaMA. Here, not LLaMA. 0 out of 4. So math, it is not that good. When it comes to code generation, programming, we have human eval, which is by OpenAI, and we have another task, MBPP here. Palm comes out here for, I think this means how many generations you do until you find some that is good. Not LLaMA, but here's LLaMA, there's LLaMA, and there's LLaMA, also 1 out of 3. So it's better in programming than in mathematical reasoning. Massive multitask understanding. 5-shot accuracy. Sorry. I have to come back to this one. Here's a big question mark. Because only compares to Lambda and Palm. What's missing here is comparison to, well, Codex. Where's the programming language model by OpenAI? It's not here. Codex, we need that one. But well, I think this paper is a little older. And now today, we would also ask for comparisons with ChatGPT. How well does it compare to ChatGPT? But maybe we have to wait for another couple of months. And then we have the massive multitask, language understanding, 5-shot accuracy. Again, 1, 2, 3, 4. Is it the average? No, it's the average. Couple of tasks. We see not LLaMA, not LLaMA, not LLaMA, not LLaMA, not LLaMA. But when we compare the numbers, still something to learn. Then instruction fine-tuning. Okay, another things, 5-shot comparison of model, moderate size with end. Here, LLaMA comes out top. Still fine. Okay, so this is a really, really strong part of the paper where we see that LLaMA is good in a couple of, well, in quite a lot of tests, but there are a few tests where it still is, where it's not state of the art. It's a good result for a paper and makes me quite happy, because at the end of the day, we talk about a neural network that can be trained with a couple of optimizations, efficiency optimizations that everyone can do on data sets that are available to everyone. There seems to be no big secrets in there. Instruction fine-tuning, bias and toxicity and misinformation, how it behaves and so on and so forth. Like analysis when it comes to AI ethics, also carbon footprint, very nice to know how much tons of carbon dioxide equivalent was generated. Quite okay. So this makes me quite happy. We have another paper here where people trained a model using quite a lot of, I'm going to say, optimization strategies in order to make the neural network smaller and more efficient, which is useful. Again, shorter training, smaller carbon footprint, inference is faster, more people can use it. This is quite good. So it's a nice paper. Please feel invited to also have a look at this paper. Now, I have to come back to something else. Maybe you already heard this, me discussing. There are a few things that I'm most interested in. So LLaMA, open and efficient language models. How open is this model? Let's have a look. How open is this model? When we go to the GitHub repository, then we can see, it's very interesting. This repository is intended as a minimal, hackable, and readable example to load LLaMA models and run inference. So for me, as someone who does this on a daily basis, I usually look at the code. So there's LLaMA, there's a LLaMA model. Let's see, okay. PyTorch, model arguments, RMS norms, normalization, couple of tensor operations. There's the attention itself, column, parallel, linear, and so on and so forth. So this is the layer for the multi-head attention. Then there's feed-forward. Yes, there are feed-forward layers in the transformer architecture. Then we have transformer blocks, building them out of attention and feed-forward and using no normalization. To anyone who is working in that field and has implemented the transformer architecture and knows the way around, this is absolutely no surprise. At the end of the day, the transformer architecture is only big. It is not complicated or complex. It's just a very simple pattern that uses attention and normalization, skip connections, and feed forward layers. It's nothing really, really complicated. You just stack a lot of those decoders or encoders on top of each other. Okay, so we see here is the model itself. What else do we have? The tokenizer. It's how to the sentence piece tokenizer, mapping strings to tokens that you can then run, that you can then input or put users inputs for your neural network. How to load it from some model. And also the generation, which is also not that complicated, where you have a prompt or a list of prompts, you do some batch processing, and then you generate the next tokens until you hit a finishing conditions, like number of tokens to generate. This is also, for people who work this, not really a surprise, nothing new in there. But when we lean back and see that, well, okay, maybe something is missing. This is all for generation, loading the model, loading the tokenizer. And here comes the crucial part. LLaMA models and run inference. In order to download the checkpoints and tokenizer, fill this Google form. Is where the sadness starts. LLaMA is available to researchers only. So you have to fill the Google form and put in a couple of papers that you have published, and then they might give you access. So this is not really open. It means that the model itself is open to research. What's also missing in here, this is just inference. What I have not seen yet, and maybe you know, so please tell me in the comments if you find it. What's definitely missing is dataset preparation. Like I say in the paper, what they do with the different datasets in order to optimize them slightly. The dataset preparation script, well, I do not see it right here. Maybe it's in another repository, but so far I could not find it. And when we talk about model training, training the model itself is not in this repository. I have not seen another repository about model training. So this also does not seem to be that open. And finally, model evaluation, running those benchmarks with different data sets, also not available, at least not in this repository, and I have not seen another repository. So I hope that I am not wrong, but if I'm right, then this is not really an open neural network. The only thing that is open is if you are in academia, if you are a researcher, you would get access to the model weights. But training, don't see it yet. Evaluation, I don't see it yet. Data pre-processing, I don't see it yet. So I hope that Meta is going to publish this as well. This would definitely help in democratizing this whole neural network thing. I always remember when talking about these things that models like Megatron is available. Everything that you need, you can train your neural networks using that. Here, there's no training whatsoever. So to the best of my knowledge today, there is an open model available, but open means that you can only download the trainable parameters, the pre-trained parameters, the model weights if you are a researcher. You cannot do fine-tuning. They don't have any source code for you to reconstruct, to recreate the whole experiments. Makes me a little bit sad. Well, so please, if I'm wrong, let me know in the comments. I would love to see all the missing things. And this is the training, the pre-processing, and the evaluation somewhere else. Well, and I also would love to see that more people can actually use these things in inference and then build great tools from that. Remember, Stable Diffusion made a really, really big difference in the moment that they published this neural network for everyone to use. And I hope to see these with more and more large language models. Thank you very much.